Good afternoon. I hope everyone's doing well. We are actually on our last webinar of our deeper dive. This one is IPC, which is the Integrated Physics and Chemistry. This one was written with the TEKS in mind, but a lot of them work obviously for other state standards. I am Krista Sampson, and I am here with Vic Sampson, the author and presenter today. And there we go. Thank you. And I will hand it over to him. He's just going to show you how to use the system and then jump into IPC.
Work on it. So let's talk a little bit about IPC. So in the IPC that we call it here in Texas, it's an integrated physics and chemistry course. And the idea behind this is you get a little bit of physics, a little bit of chemistry, but it tends to be more conceptual than the regular general chemistry or general physics. So in here, we've got 8 different investigations, 4 for physics, 4 for chemistry. You can see where those are here in the book with the table and contents. I thought today, the other thing you can do when you're looking at all of these resources, since it's both integrated physics and chemistry, if you're teaching a course like that, you can also pull ideas from chemistry, the chemistry book. There's a bunch of things in there that don't overlap with the integrated physics and science, physics and chemistry. You can also go to the physics book. This tends to be more mathematical than those, but there are there. Or you can move to the physical science NGSS version that's kind of set for like an 8th grade audience. So you can pull some more of those things as well from there. So you've got lots of options if you're teaching a course like this. For this today, I wanted to talk about, I think, an investigation I really kind of like. It's called defrosting trays. That's really having to do with thermal energy from a physics standpoint of how that ends up working. So let me show you how this works by kind of doing a deep dive into this investigation. So all of our investigations start off with a phenomenon that we introduce. In this case, we're going to be introducing a defrosting tray. So here's the handout for this investigation. And we introduce this phenomenon, show them a quick video, and allow students to write down some things that they notice. Not necessarily things that they're wondering about right now, but just things that they notice in the video. They can then share those ideas out with their group and then the class as whole. And then what we've designed those to be is setting this up so students will ask something related or mention something related to the guiding question. So in this case, it's how are defrosting trays able to thaw food so quickly without using an electricity? So if they say something like, wow, it really went faster with the defrosting tray than a plate, then you're like, well, that's what we're going to figure out why, right? So then we can introduce that piece with the task. From there, we ask students to create a model that they can use to answer that question at first. What do you think is going to happen? What's going on there? They share those models out with the rest of their group. As they're sharing, they're going to realize there's gaps or limitations in the model that they came up, and that uncertainty is going to lead to a bunch of new questions. Those questions then, as a group, they come up with a list of things that they need to know more about to be able to answer the guiding question. And then that stimulates moving into the next phase, which is the ideas phase, where we introduce some science ideas that help figure them out. That'll answer a lot of those initial questions they have. When you purchase one of these books, it also comes with a book code, and you can use that book code to bring all of the investigations into a personal library in our learning hub. So if you go to adilearninghub.com, you can create a free teacher account. It's just your name and your email address. Once that's created, it'll ask you for a book code. You enter that book code, and then you have all those investigations in your library from the book that you purchased. Now, what's nice about that is you got 2 things that are really helpful. One is you can download all the handouts that are in the book for students, so you don't have to photocopy them out of the book. And you can also, if you want them in color, you can have them in color that way. Second includes all the videos that we mention in the handouts or in the teacher notes that you can show you so you don't have to track these down or have a CD or whatever or a thumb drive or some shared Google Drive. It's just all there for you. So this is a picture of what we call the presentation mode, and you can use the presentation mode. That's what has all the videos and all of those things in it to as a slide deck to guide students through the investigation. So this is a picture of the first activity of the task stage. And you can shine this up on a screen, guide students through it, read the text aloud, and then you can show them the phenomenon video. Let me show you what that looks like for this investigation.
About chicken, beef, and fish in less than 60 minutes. There are no plugs or attachments. So how does it work? The tray is made of a high-density aluminum alloy, and that is the secret to defrosting your food faster. So let's see if it works. Our first test, an ice cube. Within a minute, our ice on the tray turned into a small puddle. The ice cube on the plate was still melting after 3 minutes. So far, so good. Now to the real tests: boneless chicken thighs, beef patties, and fish. The infomercial shows chicken thigh in just 12 minutes, depending on the thickness, of course. Ours took 45. The chicken on the plate still had frozen sections after an hour. Same with our beef patties. Here are the results after 15 minutes. On to the fish. Within 15 minutes, our fish on the tray was completely thawed. The one we let sit on the plate took twice the time. So where does the Pine Kitchen defrost tray rank on our bowl or no bowl meter? I'm going with no bowl. Although it wasn't as fast with the infomercial, it was definitely faster than the traditional method.
So that's where you catch their interest of why that actually works that way. So as well on there, we also have all of the images for like the bubbles where students are working. So then you can put this screen up and say, okay, now that you've watched that, right, what are some things that you notice? Write that down on your handout. Great way to keep everybody on the same page as you're moving through. Lots of structure for that. As I mentioned earlier, you move into the idea stage next. And so what we want to do is introduce ideas. So the first one we introduce here is just the concept of thermal energy and the idea of what that means in terms of molecular kinetic theory of matter. So we have this text, some images, and then a bubble at the bottom. And what I recommend doing is, especially when you first do this, is read this aloud to your students. And as you read it aloud, have them follow along. And then give them some time in their small groups to identify what they think is going to be useful for them answering the guiding question, right? So what is it about thermal energy that's helpful here? You can have each group of students then share out some ideas that they had. You can write those down on the board. And then after everyone's had a chance to share out, you can tell students if you've missed any of these things or you don't have any of these ideas, all the ideas that are up here, make sure you have them on that so they have a record. And it's really designed to get them to get used to pulling important information out of text and not just answering analysis questions. Later on, they can get to, after a while, they can do this completely on their own, and they don't need to have any guidance on this. But it's always kind of a nice way to kind of scaffold that when you're first doing this and moving them toward kind of higher levels of proficiency. The next idea that we introduce then is tracking how energy moves in or out of the system. So we talk about thermal energy can. How do you go about tracking that? So we introduce that idea. And then the final idea that we introduce is that materials have different physical properties. And we introduce 3 of them: density, melting point, and thermal conductivity constant. All of these things don't tell them the answer to the guiding question, but they're pieces of the puzzle that they can use. Once again, in the Learning Hub, all of these images that are in here are included in color. The nice feature, you can click on them and they blow up full screen. So I know anytime I made a copy of something of a handout, it always gets really hard to see for kids. So we really think these images are helpful for understanding these big ideas. So you can blow them up so they can see them a little easier. You can point things out. That kind of stuff. So it's all right there for you in the Learning Hub, and you can even read off of it off the screen, so the handout if you want to. After the ideas stage, you then move to the plan. The first thing you want to do in the plan stage is show the students what materials they have available. So you want to gather these up. We try to list them out for you in terms of the entire class and how much you would need for each group. What I really recommend doing is placing the objects that you have on a table, and then you can kind of hold them up and ask them, what might this be useful for? If you don't want to do that, we also include that image in the Learning Hub, so you can put that up on the screen. Saves you a day of prep of getting all the materials out if you want to go that way. Once they know what materials they have and what they could possibly use for, then they can plan out their investigation. We include these graphic organizers for them. So in this case, what's the question you're trying to answer? What observations or measurements you're going to collect? How are you going to collect them? And then how are you going to analyze them once you have them? So like, what are you going to do with them once you have those things? They can work on these plans in their groups before they move on to actually carrying out their plan. I always tell them that they have to get my signature first. So they've got that spot there. Below that, nice check-in. You can make sure they're on the right track, give them any guidance, give them a nudge in a direction. It's a nice little formative checkpoint there to help them out with that. Then once they have their plan approved, you can have them go ahead and collect their materials and carry out their investigation. So in this case, they're going to be looking at the rate of thermal energy transfer in these different materials, right? So they can use an ice cube and they can time temperature changes on the block as well as the ice cube. So I would recommend usually having a couple of these sensors there for them to use. To help them collect data, they have a spot on their handout where they can collect their observations and measurements. They can also make sense of their data. Here, usually it's better to have them create or update their model that they initially had so they can start using that information then to start creating a conceptual understanding of what's happening there. Because they already know in some ways things change at different rates. Now they're trying to put the pieces together of how are things related. So that doesn't really lend itself to graphing as much as a model will in this case. At the end of that stage, they should have a pretty concrete model and a pretty good answer to the guiding questions. So what we ask them to do is use whiteboards. They're about 2 foot by 3 foot, and ask them to generate an argument that includes a claim, their evidence for that, and their justification of their evidence. In this case, their claim would be their model, like what's happening, why is that able to melt things without electricity, what's their evidence for that? That includes the measurements that they're having or they've taken, and as well as ideas that they're pulling in to justify those ideas. Once they make their initial argument, you want to have them share those. You can do that in lots of different ways. You can do a gallery walk, a modified gallery walk. You can give them sticky notes to write comments on, any sorts of things to do that. The important thing is they're giving each other feedback and then taking that feedback and doing something with it. So on the handouts, we add a spot for them to record good ideas. So these are things like, hey, I saw a good idea on somebody else's board. We might want to consider that. Or if someone gave us, whoever was presenting their board, they got some advice to fix something, they can write that down and share it with their group. At the end of this stage, you want to make sure you give them time to use that feedback to improve their argument and make it better. That all feeds in itself, and that helps them learn how to give better feedback if there's a reason to use it. If students are struggling, we also include these extra graphics in the Learning Hub that you can put up there on the screen to remind them what goes into different spots. If you don't need it, don't use it, but they're there in case. After they've all have this figured out and they've got their kind of finalized argument, what you want to do is move into the reflect stage and have a whole class discussion where they're talking about both the important disciplinary core ideas that they were talking about or concepts, as well as how they engaged in the practices of science during this investigation. So what we recommend doing is we include using pictures to stimulate those conversations. So we include this into the Learning Hub where you can show it on the screen, where you've got a graphic here, and then you can put kids into their groups and ask them to explain what's going on in this image based on what they know about thermal energy and tracking energy moving into and out of objects. So how can you explain what's going on? Why you have thermometers in different places? Why are the thermometers changing temperature in the way that they are? What does that mean? Kids can share it out. They can talk among different groups, add on the things, challenge ideas. You can spend some time correcting any misunderstandings that are there. Really rich conversations that come out of this. Oops, wrong way. Then you want to move into encouraging kids to talk about how they engage in the practice of science. At the high school level, we really want them to focus on evidence as being the ultimate arbiter of ideas. So your evidence must be of good quality to be able to do that. So when you start thinking about what you did during your investigation to increase the confidence you have in the quality of your evidence, what could you have done to make further increase your confidence, or what led to kind of being unsure about something? And then what could we do in the future to address those potential problems so they don't happen again? And by doing these kinds of discussions, it allows kids to really learn from the mistakes they make and then internalize those